Hi everyone, welcome to IFML seminar. Today we're so happy to have Stephen Tu from USC. Stephen is an assistant prof at USC since 2020, I would say.
24.
24, really? Okay. Okay, 24, and he is PhD at UC Berkeley with Ben, and he has been doing some amazing work at the intersection of control theory, statistical learning, and I would say optimization. I know his work a lot through several papers. I'm familiar with his work, and I'm quite happy to have him here today. And today we're going to learn about one of his recent line of works on learning from many trajectories. Happy to have you here, and the stage is all yours.
All right, thank you. Thanks for the introduction, and thanks for being here, everyone. I'm excited to talk today about learning from many trajectories. So let's get started. Okay, cool. All right, so I want to first discuss that sequential data in machine learning, specifically modern machine learning, is now not only quite commonplace, but I would say quite ubiquitous, right? So we look at various domains such as in robot learning, right? Obviously, we can't not mention things like LLMs and large language data sets and large code data sets, but also other domains like in biology, where we look at time series data, and in dynamical systems, right? So what's common here in all these different domains and applications is that this data is inherently sequential in nature. And so in response to this, a lot of the models and loss functions that are currently being deployed at scale have also adapted to this and become quite sequential, right? So starting with things like RNNs, and then moving on to transformers and state space models, right? These especially models at the bottom are driving sort of the very a lot of the recent advances in machine learning, right? So these are really sequential models at heart, right? In order to train these models, right, the loss functions that we look at are also sequential in nature, right? So if we look at our next token prediction objective, right, that is a sequential problem. Things like system identification, behavior cloning in robotics, latent dynamics learning in reinforcement learning, and also things like PPO and GRPO for fine-tuning LLMs, right? These are very sequential objects. So under this landscape, one thing that I want to discuss today is what are our current learning paradigms in statistical learning theory, and how do they relate to this landscape, right? So in statistical learning theory, we typically often think of two sides of the spectrum, right? So this is a little bit of oversimplification, but just bear with me for a moment. So this spectrum works as follows, right? So on the one hand, we have this very textbook-like a setting. This is kind of the first thing you learn in a stat learning class, right? So data comes to you independent and often usually i.i.d. And you can prove a lot of really beautiful theorems in this type of setup. Now, on the flip side, if you want to say, okay, I don't want data to be i.i.d, I want data to have some sort of correlation in it, there's this other side of the spectrum where it says, all right, instead of data being i.i.d, let's say that data is coming from some arbitrary stochastic process with possibly many correlations, and what kind of results can we prove about that setting, right? So these are the two spectrums that have been studied quite a bit, but I want to argue now that modern machine learning is actually sitting somewhere in between these two ends of the spectrum. So let me give you one of my favorite examples of this. So in robot imitation learning, or sort of reinforcement learning, what do? Let's say we want to teach a robot a task or a new behavior. Well, what we do is then we go and actually painstakingly collect a lot of data from different initial conditions, different robot embodiments, different sort of configurations on say the workspace, and we just have to collect all these what we consider many short independent trajectories, where within the trajectory could be a lot of interesting behavior, but across the trajectories a model for this of independence is actually a pretty reasonable one, right? And this is not just only the case with robot trajectories, but this happens with sort of documents across the internet, users, transcripts / chat logs, system logs, FSD logs, and sort of maybe sort of sensor reading from a disparate amount of sensors. So if we now go back and revisit this spectrum that I showed a previous slide ago, or a couple of slides ago, we see that, okay, on the left-hand side, we have this classic i.i.d setting. On the right-hand side, we have this very long, sort of infinitely long single trajectory in process. What we want to consider in this talk is this intermediate regime, which corresponds to the examples I just showed, where we have many independent trajectories, where across the trajectories, we sort of explicitly break their correlations, but then we preserve the correlations that happen within each one of these individual units here. And here I'm showing this picture with every trajectory being the same length. That's just for simplicity. Obviously, in real world applications, these lengths are going to be varying. Okay, so in this talk, we're going to focus on this, making this paradigm explicit and seeing what kind of conclusions that we can get by sort of imposing this structure in the middle. All right, so I'm going to now introduce the basic problem setup and give some notation for what we're going to talk about today. So our first object is going to be this trajectory distribution. So this is a distribution over, we could say, elements z1 to zt from this distribution here. And here I'm being a little bit vague about what zt is. We can think of them as, say, labeled pairs, sort of covariates xt and responses yt. Or we could think of them as, say, states evolving a dynamical system. We'll keep it abstract here so we can cover both of these settings in the sequel. All right. Now, what is our training data set going to look like? Well, we're going to assume we have access to m trajectories drawn from this trajectory distribution. So there's going to be m of these, and each one of these trajectories is going to be an i.i.d. draw from this trajectory distribution upstairs. Now, again, as I said on the previous slide, for simplicity, I'm just going to assume that every trajectory has the same length, although in practice, this would actually be of varying length. All right. So we're going to collect all the data we see into this trajectory data set script D. And we want to note here that means that the total amount of data that the learner sees is actually of the size m, the number of trajectories, times t, the trajectory length. All right. So what do we do with this data? Well, we now can do our usual empirical risk minimization. So we want to minimize some loss function over this data set over some function class script f. And so then the goal then is we want to control excess risk of this ERM estimator. So we're going to look at the excess risk of f hat, which is the performance on a new trajectory of the model that we learned compared to the best that we can do in class, which is on the right-hand side. Yes.
So if you look at a long reinforcement learning training process, right? Then I sample some trajectories, right? But then I use these trajectories to update my policy's parameters, and then I sample more trajectories based on this updated policy. Right? So that means that the later trajectories are not independent of the earlier ones.
Right.
So are you looking at kind of smaller chunks of the training, or?
So yeah, this model doesn't quite cover that. So that's exactly, you're exactly right in the sort of an RL setting. You would couple, if your parameters would be sort of dependent on the things that you had in the past, so you wouldn't really be in the setting, right? Here I'm just kind of looking at the data that is naturally collected for training, right? Not actually what happens in the training dynamics. Right. Good question. Okay, so that's the setup we're going to look at. So now with this setup in mind, let's establish a few baselines, right? Because we want to see what our current tools can give us access to in this explicit setup. So the first thing we can do is what I call an i.i.d. reduction. And that's a simple reduction where we take each one of these independent units, or sorry, each one of these trajectory units, and we treat them as an independent unit. So we group each one of these elements or these trajectories, and we call them, say, Z1 all the way to Zm. And then we take this data and we feed it into our favorite i.i.d. result, right? Using these boundaries that we've drawn. And so what happens if we do this? Well, we get something that looks like the excess risk, this estimator, scales as order of complexity of the function class divided by m. So this is a very stylized result, right? So then, like, obviously, there's for instance, I'm assuming that we're kind of in this fast rate regime, so there's not a square root. But this is kind of a stylized result of what happens when we do this type of i.i.d. reduction. Now, so what are the pros of this? Well, this reduction is really nice because it doesn't assume anything about the sort of correlations in each one of these trajectories, right? It just treats them as a black box, and so it's agnostic to the dependency structure of each one of these individual trajectories. So that's really powerful. Now, obviously, the con of doing something like this is that this final rate, the effective sample size, so the thing that appears in the denominator, is only m, which is the number of trajectories, instead of m times t, which is the total data set size, right? So remember, the data set size is actually, t times is m times t, and we don't actually see that reflected in this rate because of the way we've done this reduction. Okay, so that's not exactly desirable, and we want to see if we can improve this in some regard. So another way of doing this reduction is to use some of these single trajectory results and see if we can kind of shoehorn our multi-trajectory setting into this framework. So this is actually pretty simple to do, right? Because a single trajectory is is sort of the most general case. So we can kind of just pretend that we have one single trajectory and just we just stack them all together sequentially like this, and then we can then feed this into our favorite single trajectory result and see what kind of bound we get. Now, if we do this, we get something where there is an improvement, right? So now that the excess risk is going to scale as order of complexity of f divided by, and now the effective sample size has something that looks closer to the amount of data we observe, so that's m times t. But unfortunately, what happens though is that the sample size is deflated by this kappa factor, which is the minimum of the mixing time of these individual processes, comma t. So in the worst case, if this mixing time is, say, infinite or very large, greater than t, then we take t, and then we essentially divide out the contribution of t in the in here, and so we get basically the same thing as the i.i.d. result. On the other hand, when we actually do have small mixing times, then this is an improvement over the previous result, right? And this also actually captures the i.i.d. setting, because if the mixing time is 1, then you pretty much get the same rate as if you were learning from MT-i.d. data points, right? Okay, but obviously now the problem though is that in order to ensure that kappa is small, we need to impose some extra structure on this sequence here, right? And so now the question is that going to be a reasonable assumption? All right, so what is the structure we're going to impose? So I'm just going to briefly, very quickly review what mixing is and sort of how you define it, and then we're going to discuss about what it actually implies about the trajectories we want to learn from. So there's many definitions of mixing. I'm going to just take one of the most common ones, which is this beta mixing. And all this is saying is that, so beta mixing, we start with this coefficient definition, which is indexed by a look-ahead window k. And all this says is that if I have some process, I'm at a time t, and I look at basically condition on where I am now, I look at k steps in the future. And I look at that conditional distribution, and I compare to just looking at the marginal distribution of being k steps in the future. And I want to compare these two distributions in say, total variation distance. So if I do that, then the mixing time is just defined to be roughly of the minimum window size k, such that this mixing coefficient dips below order 1 over t, right, where t is the length of the trajectory. Okay. So that's what the definition is. It basically says that if I, condition and look far enough ahead, I'm going to forget the history, right? And so this is a assumption. It does have some downsides, right? And so one of the downsides is that it's very difficult to actually estimate or verify this assumption, right? So if I just give you a bunch of data points and I ask you what is the mixing time of this, the data that I collect, well, that's actually that's not that easy to estimate. Second of all, if I write to a dynamical system and I ask you to analyze the mixing time, depending on the complexity of the dynamical system, that can be a paper in and of itself, right? That could sort of be a very non-trivial problem to even estimate the mixing time, right? Let alone do it sort of, optimally or get a very sharp handle on it. Right, so that's one challenge. Now, another challenge is that there's actually a lot of processes that we want to learn from. So things like unstable, chaotic, periodic systems that don't mix, right? So not only can this property be difficult to estimate, it can also just not hold for many processes. Another example, something like in human dialogue, right? If you're talking to someone and they're like a mixing sort of a conversationalist, right? So basically what that means is that after maybe 2 rounds, they'll just forget everything you said in the past, which is not the most fun conversation to partake in. Right, so that's if we want to sort of learn from we're interested in human dialogues, right? Then that's not really a good assumption here. Okay, so now then this sets the framework for this talk. Can we do better, right? So what have we seen so far? Well, we've seen sort of opposite ends of the spectrum. So on the one end of the spectrum, we want to make no assumptions about this process that we're drawing trajectories from, and we get a rate that discards sort of the length of the trajectory on the right-hand side. On the other hand, we look at the other side of this spectrum where we assume some strong bounded mixing times for this process, we get something that's closer to what we want, but then there's a very strong assumption there. So then the question is, can we utilize this multiple trajectory structure that we discussed in the previous slides to improve these rates, right? So for instance, can we show that there are certain situations for which the excess risk scales as the complexity of the function class divided by all the data we have, even in a regime where the mixing time could be infinite, so that kappa equals t, right? So are there regimes for which we can do this? And also, can we do this in sort of an optimal way, right? So for a particular problem, can we give you something that approaches an instance optimal rate for that problem? So that's going to be the backdrop of this talk. Are there any questions before we dig into the more technical content? Yes.
Could you elaborate more on the i.i.d reduction? Like, what does that exactly mean when you say it's complexity of F over M? Do you just learn from a single trajectory as an average time across?
So there's a couple ways you can do this. Sort of the most naive one is you have MT, right? So for each trajectory, you say only take one data point, right? That's sort of the most naive thing you can do. Now you can sort of say, well, that was dumb. Why don't I use all the data? Well, if you use all the data, right, you basically, in calling an i.i.d result, instead of having, say, one of the points be your covariate or your z, right, you take the entire trajectory as one unit of independence, right? So in that case, depending on pretty much most results you use, you're going to get, actually, I think after I'll say it with an asterisk and we can talk about this offline, but basically every result you use with a small asterisk is going to give you this result where you only basically see effective sample size as the number of independent units that you pass to the i.i.d result. So even though your unit is of t length, right, you don't really get the benefits of that when you use this reduction.
Not even like T over kappa factors or...
So T over kappa comes from, right, you need to use more of a one of these like single trajectory results that actually tries to create independence by using the mixing time, right? So if you had a mixing time, you can improve that by using one of these blocking arguments to create independence. And that's how you get this MT over kappa factor.
For example, N is 1, and isn't it the case that both of the settings are good? So...
If M is 1, right. Okay. So they are right. I mean, the data they're seeing is the same, right? But it's just the analysis is different, right? Like the reduction, won't sort of actually do the blocking argument in the left hand side to actually give you the T over kappa. Whereas, yeah. If you want to think about it in this way, like this is sort of the most general result, right? Like basically. This meaning that this generalizes the left hand side, right? Because you can always say kappa to be 1, and that would recover the i.i.d result, right? So really, like I said, there were two reductions, but you can actually say that this is the most general reduction on the right hand side. Okay. Any other questions? Yes.
So I didn't quite understand how this mixing time. So let's say you got something simple like the OU process. Do you have a mixing? Can you calculate what the mixing time is?
Something like xt plus 1 is like just xt plus Gaussian noise.
Yeah.
Yeah, that doesn't mix.
That doesn't.
Right.
Okay.
Yeah. So for a linear dynamical system, it mixes when the transition matrix is what's called stable. So meaning the spectral radius is strictly less than 1. Yes.
So your function is a function of t length trajectory.
In this, okay, so that was a little bit. I kind of made that a little bit vague. Right. There's two ways you could imagine this, right? Like, so you could say I'm gonna in the first part of the talk, right? It's actually going to be a function of only zt, right? So it's basically you can think of the process as like a bunch of states, and you want to sort of make a prediction about, say, the next state given the current state, right? But you can also have the function like taken all the trajectory. We'll see that in the later.
Then it makes sense because if it's a function of t length things, then the whole thing makes less sense. But
right, right, yeah. We'll get back to so in the later part of the talk, it's actually going to parameterize an entire trajectory distribution. But yeah, we'll see that. We'll come back to that in a moment. Yes.
In your complexity term, are you also taking into account the distributional function? Like, what is should it like the distributional thing should go somewhere, or those are just constants here?
What do you mean the distributional? Which distributional assumption?
Y could be some function of X, right? Like what is the assumption on?
Oh, you're talking about like
Z right now.
yeah. So in these stylized results, let's say like we are Z's X, Y, then maybe we'll just assume that like Y is say F of ZT plus some noise, right?
So the noise term, where does that go? Where does the noise term go here?
That's kind of like hidden in the complexity, I would say.
That's a function plus. Oh, yeah,
Yeah, so that's basically like that, in sort of a nonlinear regression, that would maybe appear like a standard deviation term in the front, and we just kind of hide that. Yeah, because that part is not the part we want to study, right? Like the Y condition on X distribution, we're not going to study that. So we kind of abstract that away here. Okay. All right, so I'm going to now talk about the first setting for which we can say some interesting things about this intermediate framework. And maybe it's not surprising that this setting that we can say some things, pretty strong things actually, is the linear regression setting. All right, so here now I'm going to make the process a little bit more concrete. So I'm going to assume I'm in a world where the Z's are labeled pairs. So we have these covariates X and these responses Y. The covariates are generated by linear dynamical system that an LDS. So this is the xt plus 1 is some linear function or linear matrix A or matrix A times xp plus noise. And then the response is also going to be a linear response based on X plus some corrupting noise xi. Okay. The thing that we're going to do here that maybe deviates from standard linear regression is that the response is going to be a vector value response. And so that means that WT is actually, W star is actually a matrix and not just a vector here. But that's just because I want to be able to cover a setting where we do things like system identification of A. Right. So if you want to think of, you can just pretend T is a scalar and then it looks more like standard linear regression. Okay. So here, the ERM, the empirical risk minimizer over linear functions and square loss, well, that's the very nice solving the normal equation. So you get the formulas that you expect. Again, the reason why it's maybe the opposite order which you expect is because we're trying to optimize for a matrix here and not just a vector. But it's really the same thing, right? So it's like the YTX times XTX inverse. Okay. And the excess risk in this setting is just the parameter error. So W hat minus W star, but weighted in this metric, which averages the covariance matrices along the entire trajectory. So we take the sum from T1 to capital T of all the covariance matrices, and that forms the Frobenius norm, the weight of the Frobenius norm, the weighted of how we measure the parameter error. Okay. So for simplicity, we're going to assume for this talk, like in our paper, we can adjust these noise assumptions, but just for this talk, let's just assume that WT is normal zero identity. And then this response variable conditioned on the history is going to be zero mean and sub-Gaussian, right? So what that means is that this the xi-t sequence here actually forms a martingale different sequel, different sequel, different sequel, with respect to or noise.
Simple question. All the trajectories are started at the same point. It's irrelevant.
They can start from a random x0. Yeah.
Just start x0, follow this dynamic, and the noises are that's it.
Yeah.
But the A is fixed.
The A is fixed, right? The A is the same generating process for every trajectory. Correct. Okay. So again, as I mentioned before, the only reason we post this MDS structure is because we want to be able to come up to a setting or cover a setting where we actually recover the underlying A dynamics, because that corresponds to system identification, which is a key primitive in controls, and which a field that I do a lot of work in. So why I wanted to do that. Okay, so now we're going to collect the noise variables in this matrix xi-t. Okay, so far this is just some notation and setting up some assumptions here. All right, so what's the beautiful thing about linear regression is that the error analysis can be done almost in closed form, right? So if we look at the delta matrix, which is the difference of the parameter errors, we get these two terms here, right? So this brown color term is one, and then we separate the XTX inverse into a 1/2 on the left and then a minus one, sorry, minus 1/2 on the left and a minus 1/2 on the right in blue. Now, why do we do this? Well, so the first term, because of that martingale structure, is actually has, and the way that we've weighted it with minus 1/2 of xtx forms what's known as a self-normalized martingale, right? So there's a really beautiful result, actually dating back to a lot of the work from De La Peña, but I guess the most useful instantiation comes from Abbasi-Khoury in 2011. This is a paper studying linear bandits. And they show, or extensions of this result can actually control this self-normalized martingale term by just square root of the sum of the dimensions of the matrices that we want, of the matrix we want to recover. So square root m plus p. Okay, so that part is good. It doesn't need any trajectory assumptions for this to hold. Like, this is actually a very general result. Now, the problem though comes when we want to look at this minimum eigenvalue term. So analyzing this minimum eigenvalue is much more challenging. And in many of the single trajectory analysis, this is where all the assumptions about A come into play, right? So this can include things like marginal stability or some sort of eigenvalue conditions on A that are necessary in order to control this minimum eigenvalue. Okay, so it turns out though that in this multi-trajectory setting that we consider, it is much easier to control this quantity, and actually you don't need any assumptions on A for this to happen. All right, so I'm going to give you some of this why I'm going to try to explain why it is the case. And so this will be sort of the closest I go to actually doing a proof in this talk. So this will be the most in-depth we go. So bear with me for a moment. But we're going to look at this quadratic form. So this Q of V, which is the eigenvalue of the minimum eigenvalue of the data matrix of XTX is just the minimum of the quadratic form over the unit sphere. So we're going to look at fixing an element on the unit sphere, and we're going to look at this quadratic form. Now, because of this multi-trajectory assumption, it actually decomposes into the sum over m individual quadratic forms Qi and V. So why is this important? Well, there's a key observation here. Because of we've assumed that the noise process is Gaussian, and because of the way that LDS evolves, basically the xt iterate is actually a linear function of the noise, then what that means is that this quadratic form is actually a degree 2 polynomial of Gaussian random vectors, right? And so because Gaussian polynomials have this beautiful hypercontractivity property, what that means is that if we look at the second moment of the quadratic form Qi, we can upper bound that with the square of the first moment, right? So we can take the expectation of Qi and square it. And that actually, the constant factor there, I think, is 3. And that actually gives you an upper bound, right? So Jensen's inequality tells us the reverse, right? Jensen says that we can lower bound E of Qi squared by the expected value of Qi and then taking the square. But this hypercontractivity allows us to go in the other direction. Now, why is that key? Well, so now what we can do is use the fact that we have multiple trajectories, and we can apply one of these one-sided Bernstein inequalities for non-negative random variables, right? So if we look at normalizing the quadratic form on the left-hand side by a one-sided Bernstein, M inverse Q is lower bounded by the expectation of Q1, and it's Q1 here because these are all i.i.d, so we might as well take the first one, minus a square root term that depends on the second moment of Q1 times M inverse, right? So this first inequality comes from one-sided Bernstein. But then if we then chain this together with this hypercontractivity condition, we actually get something that looks like 1 minus square root 1 over m, I ignore the log factor for the moment, times the mean of Q1. Okay? And so then now we can use the fact that we have multiple trajectories to then select a sufficient amount of trajectories. Here is order log 1 over delta, so that we make this bound at least 1/2. Right? And so by chaining these things, we've shown here that the quadratic form with high probability is actually lower bounded by m times t times the quadratic form of the expected weight in the empirical in the x-axis risk, which is this gamma t. So remember, gamma t is the average of the covariance matrices over the entire trajectory. And all this is done with no assumptions on A, right? This Gaussian hypercontractivity assumption doesn't require that A is stable. It's just because it actually doesn't have any sort of requirement of that form. So that allows us to actually relax all the assumptions on A. And to finish this argument, as I said, this is just for a fixed unit vector. Well, you can make this work for every unit vector over the sphere with an appropriate covering argument. Some care needs to be done here, but you can do it in a way that you don't have to introduce any new assumptions on A, right? And so here we see that actually this multi-trajectory assumption allows us to make more progress here than you can do in the single trajectory case. Okay, any questions on this? Yes.
For the single trajectory case, what are the assumptions on it and guarantee the minimum?
What are assumptions on A?
Yeah.
Yeah, so this is a good question. So the easiest one is that it's stable. You can actually make it marginally stable, which means that spectral radius of A is equal to 1 with a little bit extra work. And actually, there's a lot of follow-on work where you can actually take A to an unstable regime, meaning its spectral radius is greater than 1, but you need to impose some sort of conditions on the eigenvalue. I don't remember the exact conditions, but it's not all A matrices. Like there's something about like the geometric multiplicity of eigenvalues that I don't quite remember the exact conditions.
So if you write one of the settings, does it include the constant here? Like some effect has to come in, right? Like where does that come in? Like, it was good versus it was bad. So here, I guess, for the purpose of bound doesn't matter, but the constants change.
Are you asking like, can I improve this type of result based on A?
Yeah.
Good question. So right, this is sort of uniform over all A's, right? I don't know if you can. Yeah, I'm not sure. Like the best I think you could be able to do is actually sort of make this burn-in time improved, right? Like basically what's the minimum amount, but up to a constant factor, like this is exactly like what you want, right? It's not improvable, right? You're not going to make this like 300, right? So you can only make this arbitrarily close to 1. And so that means the only thing that can kind of differ here is your condition on the number of trajectories that you need that may be improvable based on A.
If A was good, then you should just.
Right. So that's exactly right. So if A was one of those cases that was handled by the previous work, then you don't need here log 1 over delta. You would just need like 1, right? Yeah. Yes.
N times T, like where did the T come from?
Where did the what?
The T, like where did we get the N times?
Yeah. So that's just because the expected value of Q1 is not normalized here, right? So the expected value of Q1 is actually just the sum of all the covariance matrices. But remember the way we define gamma T in the excess risk is actually the average, right? And it's the average that and so basically that's why there's a factor of T there. Okay. All right, so if we chain all these things together, then what do we get is that under the noise assumptions I just stated, if the number of trajectories exceeds the covariate dimension by a constant factor, then the expectation of the excess risk of W hat of MT is upper bounded by the number of parameters I want to learn, which is N times P, divided by the amount of data I see, which is M times T, right? So this is pretty much the optimal rate up to constants, right? Like this is exactly what you get when you do linear regression over MT i.i.d data points, right? So you can improve this rate in general. And also importantly, this happens irregardless of the mixing properties of A, right? So as I said before, if spectral radius of A is greater than or equal to 1, mixing time is infinite, but that doesn't matter here, right? And it's because of this multi-trajectory structure that this happens. Related to that is that if you wanted to relax this assumption and say, I want M to be, say, little o of N, so I want to look in a regime where I have fewer trajectories than order N, then this type of result is not possible. Right? So this is really truly a multi-trajectory phenomenon. Okay.
Sorry, quick question.
Yes.
Don't you require the noise in the linear regression to be i.i.d. Gaussian?
The noise is i.i.d, yes.
Right. So, I mean, isn't there some cheating a little bit going on here? Like this talk is about eliminating like the i.i.d. assumption.
Okay. So let me go back.
The noise is i.i.d.
Right. So when I say the noise is i.i.d, I mean the thing that you're injecting at every time step, right? But the XT process is not i.i.d, right?
Right, but still we can do linear regression without, I mean, there are algorithms for linear regression that don't require the noise to be i.i.d. Gaussian.
And you say that they would get the same.
No, that's my question.
Yeah, or maybe like more of an agnostic setting.
Yeah,
Yeah, that's a good, but actually, I have to think, yeah, I don't know if it would recover exactly this result. I have to check on that. Any other questions? Okay. All right, so now I want to move beyond linear regression, right? Because linear regression is a nice model for analysis, but it's not a very realistic model for a lot of things we want to do in practice. So, all right, so what are we going to do now is we're going to look at a parametric family of distributions. So we're going to look at p theta here, which is parameterizing distributions over z1 to t, right? And then the theta is going to live in some parameter set, capital theta. And we're going to look in this realizable setting where the data that is generating these individual trajectories has the form of being drawn from one of these individual distributions. Okay, so the estimator we're going to consider is the maximum likelihood estimator. So we're going to take all the data we observe and then look at the max and look at and find the parameters that maximizes the sum of the log likelihood over all the data. Now, the excess risk we're going to study now is still going to be of the form of a difference between the parameters. So we're going to look at theta hat from the MLE minus theta star, which is the one that generates the data. And we're going to normalize this by matrix here, but now this matrix changes to be something that looks like the normalized form. So I bar is T inverse times I, where I of theta star is the Fisher information of this distribution evaluated at the optimal set of parameters. Now, you might say, okay, if we consider MLE to be doing ERM over log loss, then shouldn't the excess risk actually look like KL divergence between these two distributions? The answer is yes. We're writing in this form because locally KL divergence is an F divergence. So locally, you actually sort of have exact equivalence to this up to a common factor. This form is just going to be easier to compare to our previous results. So we're gonna look at this form. All right. So how do we study this problem? Well, it actually turns out that i.i.d. reduction gets us quite far here. So what does that mean? Well, there's a very nice line of work from the literature in looking at density estimation. And this dates back down actually to work from Tong Zhang and I think even earlier. But a modern version of this comes from a recent paper actually of Dylan Foster looking at behavior cloning. And what they show, or what these line of results show, is that if we just look at the maximum likelihood estimator, you get something that where the squared Hellinger distance between P star, the true data generating distribution, and your P hat is upper bounded by something that looks like log cardinality of the covering number of the distribution family divided by M, the number of trajectories we have. Now, you might say, well, doesn't this kind of defeat the whole point, because now we're back in a regime where the denominator here doesn't actually depend on T. Well, the thing is, there's a lot of information about T that's being hidden in this squared Hellinger distance, right? To emphasize, these are Hellinger distances over trajectory level distributions or path distributions, right? So there's, these distributions are actually over T elements here. So Z1 to ZT, right? And if you look at you see that square Hellinger distance is itself an F divergence. That means that locally, when the parameters are close, it actually has a nice quadratic expansion that looks like 1/4 times the error of the parameters weighted by the Fisher information at theta star plus some extra error term, right? So if you ignore that little O term, what you get is the result you actually want, which is that the excess risk of theta hat looks like something like the log covering number over MT, right? And so really the T comes out because you take a Taylor expansion to a second order of the Hellinger distance squared. Yes.
So here, data is a joint distribution of a T size object.
Yes.
And so it can be like, so its inherent complexity scales with T.
Not necessarily, right? You think of a Markov chain, right? Like
I know,
that's
but so have
yeah.
you made that, yeah, but you haven't made any assumption about that.
No.
Right? Like,
No.
yeah, so like.
So right, you're right.
Without any such assumption, how can I expect a 1 by t?
Right. So you're right. So if there were like t parameters here, then like this would basically also have a t in it that would cancel out, right? So we're going to look at assumptions, or we're going to look at cases where the complexity of that distribution doesn't grow with t, right? So think of like Markov chains or the simple attention model.
But you haven't made an explicit assumption.
I haven't made that
It's
here.
somehow hidden in some other.
That thing is going to be what you're saying is hidden right here, right? But at this level, I don't need to make that assumption yet. Comes when I actually want to instantiate this bound.
Does this also sort of work with what's the lower bound at n, or it's true for m being 1 and then?
Say again?
Does this hold for m sufficiently large, or is it true for like m equals 1 and?
Oh, so this bound doesn't have a lower bound assumption on m. Although if you're going to need m to be greater than 1 for it to be a non-vacuous bound. But yeah, the first bound doesn't have that. We'll see in a moment that in order to kind of do these expansions, that's when the assumption on m is going to come into play. I think there was a question back there.
Why this work for linear regression? Why did this now work for linear regression? This kind of argument?
It does up to some caveats that I will explain. I can explain later. Yeah, like this type of proof strategy would also work for linear regression. It unfortunately doesn't quite recover the same result, but that we're not in a position to understand where it would differ yet. But yeah, like in principle, at this level, it could. Yeah. And I was actually kind of hoping that this is like the general proof strategy, but that is not quite the case yet. Okay, so right, so then really what this says is that all we need to do, right, the task we have ahead of us is we just need to argue when we can do this local quadratic expansion, right? So to illustrate, to make very precise what we're trying to do here, so here's a graph of so we have P0 as just a scalar normal distribution with mean 1 and variance 1. We have P1 where it's variance 1 as well, but we're going to vary the theta 1 parameter. And we see two curves, right? So the first, the blue is actually what the square Hellinger distance is, and this orange curve is our quadratic approximation. And our goal then is to quantify the region for which there's an order 1 constant gap between these two. Okay. So how do we do this? Well, there are some, so basically what we show is that these two conditions need to hold, right? So the first condition says that if I take 2 points, theta 0 and theta 1, and I look at the ray along theta 0 and theta 1, what I need is that the Hellinger distance between those distributions induced along that ray is upper bounded by at most some radius condition, and that radius condition depends on, say, the fourth moments of the score function and the second moments of the observed information matrix. So the exact formulas are not that important. There's just some moment conditions that govern the size of this radius for which this expansion holds. And then the second assumption we need is some sort of relative closeness of these two Fisher informations, again, along the entire ray. So again, the actual formulas are not that important, but basically we can come up with explicit radius conditions for which this type of approximation holds up to a constant factor, right? So in fact, this constant can be made arbitrarily close to 1/4, sort of by adjusting the size of the radius by a constant factor as well. Okay, and to answer that previous question, this is kind of where that argument breaks down a little bit. Because in the case of LDS that is unstable, these moment assumptions actually grow with t, and then that kind of makes the whole argument break down. But in many situations, that is actually not the case, as we'll see in a moment, and then this argument will go through. Okay. So this gives rise to what we call the Hellinger localization framework, which is really just combining those two steps, right? So we do the step 1, which is that i.i.d. reduction. From learning density for sort of estimating densities. And then we do step 2, which is just to kind of make sure that that quadratic expansion holds. And that will impose some conditions on the amount of trajectories we have. And the tools to do this are written more explicitly in the paper. And then once we piece all these two things together, we get basically excess risk being like log of the covering number divided by the amount of data we have. Okay, so let's see some explicit examples of this. All right, so the first thing we're going to look at now is a nonlinear GLM, right? So we're going to look at this process that involves an RD, and it's just zt plus 1 is given by the application of a coordinate-wise sign activation function times of a star zt plus some Gaussian noise. Okay, and I mentioned previously, like this sign activation is applied coordinate-wise, like you would do in a neural network, right? And our goal is going to be to recover this coupling matrix A star from observations of this trajectory sequence D. Okay, so this type of model is actually pretty challenging for existing GLM analysis that happens in the single trajectory setting. And for, for starters, we don't want to assume that this coupling matrix we are trying to recover is stable, much like we didn't want to do that in the linear systems case. Reason being, because when we actually have unstable A stars, we can get some pretty cool behaviors, right? So here is one instance of a configuration in R2 where we get this like limit cycle behavior. And then the second here is another configuration of data points where you actually get something that looks kind of like this discrete mode jumping type system, right? These are all given from the same system, which is different instantiations of A star and the noise variance of W. All right. Another reason why this is challenging, this is a little less interesting, but it's still, I guess, important for technical reasons. The sign activation is not monotonic. This is an important assumption in a lot of the previous analyses. All right. So what do we show then is that we look at maximum likelihood estimation over this set of distributions parameterized by that coupling matrix A, where A lives in a norm ball of radius r. Importantly, this r can be greater than 1, so that it allows us to have unstable matrices. So as long as the number of trajectories satisfies something that scales Pauli dimension times t, then with high probability, we're going to have that the excess risk is upper bounded by O tilde, so we're going to hide some log factors here, of the number of parameters we need to recover in that coupling matrix divided by the amount of data we have, right? And so again, this is an instance where the number of parameters we have doesn't grow with the amount of data we have, so we can actually get a rate like this. Okay, we can also make this a parameter recovery bound, and by doing that, we pay an extra d squared. I don't know if this is optimal. This comes from trying to lower bound the minimum eigenvalue of that Fisher information matrix. We have an argument to do that, and that argument picks up 2 factors of d. Again, I don't know if that's actually required.
Is a quick question. You can't actually solve this ML. Like, it's
Oh,
not possible
good,
to actually
good,
find
good,
it.
good. Yes, right. So this is exactly right. So the MLE here is just I probably should have written this down, but it's just basically doing a nonlinear least squares problem. In general, it's a non-convex objective, so you possibly cannot solve this, right? But it's this is more of a statistical. Like if you could solve that MLE, this is what you would get. Right? It's good observation. Okay. Now let's turn to something else. So let's actually look at a linear attention model. So now we have a vocabulary of K tokens embedded in RD. We're going to build a generative model to generate token t plus 1 from the existing context of tokens 0 to t. And we're going to do this with a very, very simple, very toy linear attention model. And so what is this model doing? Well, on the left, we take the input tokens, so basically the current context 0 to t. We're then going to feed that and to make a attention calculation where we take the keys, and so we embed the context with keys and queries, right? So here are the keys, and then this is we're going to take qt as the query. We then do this attention computation, which is this formula here. We're going to do this with linear attention, so there's not a softmax. Usually you have a softmax here to make this probability distribution. Here, we're going to kind of give a soft normalization and just divide this by t. This is a limitation of our analysis that I would like to figure out how to remove. But it's here for the moment. And then once we form this attention scores, then we make this hidden layer, or this hidden representation by just taking the sum of this linear combination of the values of that context weighted by this attention values here. And then we make this H into a set of logits by projecting it up using this classifier head, and then we take a softmax, right? So that's a lot of pictures this is the equation, right? Maybe I should have just started with the equation. It's actually a very compact formula here, right? So it's a very toy model, right? Obviously, like no network you train in practice is going to look this simple, but let's just see what we can do with this toy model. Okay, so our goal here is going to be to identify this key query product matrix. So this Q times K transpose. We're going to vectorize things just to allow us to kind of be in this more vectorized model that we stated previously. So this is going to be a D square dimensional vector. So here D is the embedding dimension that we use in our attention model. And we're going to make some technical simplifications. We're going to absorb the value matrix into the classifier head because our goal is to just predict to recover KQ, right? So we're not going to try to recover B. We're also going to do this thing to make this problem identifiable, where instead of having the classifier head produce K logits, we're going to produce K minus 1 logits and tie the Kth logits to be 0. This is just because softmax is sort of non-unique up to an affine transformation, where if I just add C to every logit value, I get the same distribution, right? So in order to kind of make this non-identifiability go away, we're just going to actually predict logits in K minus 1, and then that gives us the distribution that we want that's identifiable. Now, these two are sort of in a way without loss of generality under the setup. There's one extra assumption here is that when we form these keys and values, we're going to use 0 to T minus 1, right? We're not going to put 0 to T here. This is just to make it so that we don't have to calculate higher order moments of ZT. Yeah, I think we can remove this. We just need to do it. All right. Okay. So what do we get? Well, so what's our model here? We're going to look at, again, next token prediction or maximum likelihood estimation. And so what we prove here is using this framework here. So suppose that the embeddings of our vocabulary, so we can think of taking a K by D matrix of embeddings where each row corresponds to the embedding vector for that token. And also the classifier head C is going to be here in this case, K minus 1 by D matrix. Suppose that both of these have full column rank. And now if we have this quantity M0 here, which scales polynomially in both the vocabulary length, the 1 over the minimum eigenvalues of this embedding and classifier head, and unfortunately exponential in R and the operator on the classifier head. I'm not sure how to remove this factor here. So it's going to be here for the on the slide. And so, okay, under this prefactor here, basically we need the number of trajectories to scale as D squared times this prefactor. And we also impose this assumption that the length of the generation is at least this prefactor, right? So under this setting, so you can really think of these as kind of like a very pessimistic burn-in time. But once we pass this very pessimistic burn-in time, we get the result of the following, that the estimator, so the excess risk of the next token prediction result here, theta hat, has that same value we saw before, which is the parameter count divided by the amount of data. And also, again, this is a case where even though that this model actually depends on the entire history, it's parameterized in a way, right, just to make this point clear, right? This model is like, it's not a Markovian model, right? Like the generation depends on the entire history, but the parameters for that generation are actually order 1, right? They don't scale with time. Okay. All right, so those are the two models I want to show in this talk. There's other examples in this paper looking at mixtures of Markov chains and also linear regression problems under more general non-square losses. I'll defer that to the paper. I want to briefly talk about what are some sort of things we could do to extend some of this work. So I think the most obvious thing is to build more realistic models, right? Admittedly, the kind of attention mechanisms that we're studying here are very simple, right? They're linear attention, they're single layers, right? To what extent can we actually pool these into more realistic models, and what can we say about these more realistic models? I think another interesting avenue to explore is looking at non-sequential dependency structures, right? So the MLE kind of framework we developed, right, like it is actually in a way agnostic to the dependency structure of that individual trajectory. So you could imagine, for instance, things like icing models or graphical structures where it's not about temporal correlations, but other more structural correlations. So can we apply some of that machinery to study these problems? And finally, you know,
That's a protein. That's a protein.
yeah. Finally, I made this for you, so, yeah. So finally, can we now apply this type of stuff to look at more controls problems? So things like filtering, which you can think of as a latent estimation problem, latent estimation maximum likelihood problem, control-oriented exploration, active learning, and so on, right? So what do these type of bounds have to say about control, right? Bear with me for one moment. I want to make a shameless plug for L4DC. So if you're interested in these type of problems that sit at the intersection of learning dynamics and control, I highly encourage you to attend L4DC, which we hosted at USC next summer. So this is a growing community that really sits at the intersection. We have this exciting thing this year where we're co-located with this upcoming conference on neural symbolic systems, which is called NEWS. We're also co-located with FIFA World Cup. So that was intentional. So if you want to come watch FIFA World Cup, you can also come to L4DC. And also opportunity to hang out in LA in the summer where it's it does get to the upper 90s, but not over 100, not most days. So
Too cold.
yeah, too cold. Okay. So yeah, that's all I have. Thanks everyone for your attention, and I'll wrap up here.